So today my plan is to give you a concrete example of the vague theory I gave you yesterday, of at least the idea of trying to find the unirational variety using sub-varieties of the Hilbert scheme of rational curves. And just to be sincere, this is not just a toy example and I have a big, huge theory behind this. This is essentially the only example in which I am able to work all through the program. Okay, so this will be examples of threefold conic bundles. So before doing this, let me just recall you a theorem that we saw yesterday in the afternoon, which is the very nice theorem of Greber-Harry star. So we have this theorem. I will write it on the blackboard in a slightly different way from yesterday afternoon. So let X over B a family of rationally connected varieties, and assume that the dimension of B is 1. Okay? Then there exists a section of pi through the general point. And this is really the point interesting from my point of view. That is not only, you know, that's, as was said yesterday, is a kind of a generalization of a Zen theorem to the case of rationally connected varieties, but here really we have not only one point, but we have a dense set of points, okay? And for Zen theorem, you actually have a situation in which you really have only a unique point in the family. So this is really a big difference between Zen. And so I plan to use this to study unirationality of threefold conic bundles. And let me just start saying what a threefold conic bundle is, so what a conic bundle is. So so the definition I'm going to give is usually the definition of standard conic bundles, but since these are the only conic bundles we will see in the lecture, I will only write them conic bundle afterwards. So a standard conic bundle, so is a flat map morphism, let's say from X onto W, such that so everything is smooth, so both X and W are smooth. The dimension of X is equal to the dimension of W plus 1. So the relative dimension of the fiber is 1. And the anti-canonical class is relatively ample. And actually, this is not something I really need, but that's the standard definition. So the relative Picard group is 1. So the rank of the Picard group of X over W is equal to 1. Okay, this is a sort of minimality condition. This is a special case of Mori fiber spaces introduced yesterday in another talk. Okay. And so, for instance, let me just give an example in which we know everything about So remark, if the dimension of X is 2, so X is a surface, then we know exactly what X is. So in this case, X is just the blow-up of finitely many points in distinct fibers of a segregated Zebrook surface. So X is the blow-up of finitely many points on some Fe in such a way that you have not 2 points on the same fiber. That, let me say, of finitely many points y, such that, let me put it in this way, so the cardinality of pi of y is equal to the cardinality of y. Okay? So you can only blow up points in different fibers, and then these are the unique conic bundles in dimension 2. Remember that I'm working over C, okay? I mean, this could be empty. Sorry, thank you very much. So here I'm going a bit fast. So with W isomorphic to P1. Otherwise, the base is a generic curve. Thank you. So that's the case I'm interested in. Mm-hmm. That, as I said, this condition is kind of minimality, and so if you drop this, you have something like that. If you assume rank Picard rank relative Picard rank equal to 1, then you have y equal to the empty case. Okay, so eventually empty. As we will see, my idea is to use this essentially classification to study threefolds. So let me go in this direction. So let me plan. So plan of study unirationality of threefold conic bundles. So the first step is the following. So translate unirationality with rational connection okay, and that's what we are going to do now. Okay, so let pi from X to W be a threefold conic bundle. Okay, and assume there exists a base point free pencil of rational curves, let me call it lambda, on W. As we'll see, so I'm going to do some assumption on W, but we will see that these are essentially not very difficult to be satisfied, and essentially are satisfied in any condition, in any case that we are interested in. Okay? So using the morphism induced by this pencil, we have the map onto W, and we have a map onto P1 given by the pencil lambda. So let me call it phi of lambda. And so we have a map psi onto P1 from X. Okay. And if we consider the general point X inside here, over here I have a surface S of X. Okay. So in the definition I have on top there, so conic bundle, so these are called conic bundle because essentially you can always embed them as conics over a relative projective space over the base. And in particular, inside W, so inside W, there is what is called a discriminant curve. Delta that parameterizes the non-smooth fibers of X, of pi. So since my pencil is locally free, what I expect is that Sx, so Sx is a conic bundle of dimension 2, so with delta dot lambda reducible fibers. Let me call this delta. Okay. So the general fiber of psi is just a conic bundle of this type. And so moreover, so if we consider the generic fiber as eta, and we take the closure, the algebraic closure of this fiber, so it's such that its algebraic closure as we call it S bar is again a conic bundle in dimension 2. And what does this mean? That is, there exists an E, non-negative, such that our S bar is the blow-up of Fe in a set of points, of delta points outside the special section with a negative self-intersection. So what do I mean by this? So the Fe, oops. So this is our Fe. Inside Fe there is a unique curve with negative self-intersection, and we can always realize this S bar as the blow-up of this Fe infinitely many points outside this C naught. Okay. So the main problem here is that I can't have a similar statement for S eta. Okay. So the generic fiber is in general not the blow-up of Fe over the field, no? Because here I am on an algebraically non-closed field. And so usually, to approach the unirationality of this variety, of this threefold, you tend to study this surface over the non-algebraically closed field, that in this case is just C of t, and try to work it out somehow, some method to understand if this is unirational or not. So my point of view is that since I'm not that good in a non-algebraically closed field, I prefer to pay a different price. Okay, so here you see you want to study the unirationality of a threefold, and you pay the price to, so you lower the dimension, you pass to a surface, but you pay the price that your surface is not on an algebraically closed field. This is the price I don't want to pay. The price I want to pay is that instead of looking at a surface Sx, I want to look at its Hilbert scheme of rational curves. Okay, that's the price I want to pay. Okay, so the point that I want to make here is that clearly this description is not true on S eta, but it is true on Sx. Because, of course, the Galois action of the algebraic closure sends a curve with self-intersection minus c to a curve of self-intersection minus c. So on any Sx, I have some curve with self-intersection minus c. And so I can realize Sx as the blow-up of Fe in a bunch of delta points. The main problem is that I can't do it in a family, but one by one I can make it. Okay? So in particular, this is true on any, well, not on any, on a general. Sx inside my x. Okay? And I want to define the following sub-varieties. Of Hilbert Sx. Okay, so let me put some notation here. So so I already used the x. That's a bad notation. Okay, so let A and B be two zero-dimensional reduced schemes on Sx such that, again, as before, there is only one, I mean, I can't have 2 points of both on the same fiber, so I mean that the cardinality of the push 4 of A union B is equal to the cardinality of A union B. Okay? And I want to define the following set: R A B A D S X. If it is too small, just tell me and I'll try to write it bigger. Is it okay? Okay. So this is defined as irreducible, rational curves in I, so that's the small I, oh, okay, 2I union B to the I, I'll comment in a moment, of minus KS, oops, minus AKXS plus DF. Everything closed, and this I see it as inside the Hilbert scheme of Sx. So let me just comment on this. So I mean that I'm considering reducible rational curves inside the linear system given by this, which is minus A times the canonical class plus D times F is the fiber of the conic bundle structure. admitting a point of multiplicity 2a along my subset A and a point of multiplicity A along the subset B. Okay? So remark, since I'm taking irreducible rational curves and then I'm enclosing them, the general point of this variety represents an irreducible rational curve. Okay? So the general point, if it is not empty, of course. Represents an irreducible rational curve. And a slightly, I mean, not really important, but useful maybe remark is that these can be, so I wrote them inside the Hilbert scheme because, so I'm used to do it, but you may look at them also as sub-varieties of the Severi variety of rational curves on the surface Sx. So equivalently, we may consider this R A B A D S X as subvariety of the Severi variety. In Sx. Okay? So if you're wondering why I'm putting here 2a and a, just wait for a few minutes and I hope I'll be able to explain to you. Okay? So maybe I'll keep this one. And instead I can... Oh. Yeah? F is the fiber, sorry. Is the fiber of the rule structure. So I have a rule, so that's a conic bundle, and so that's the fiber F. Is the other generator of the Picard group of my, well, not the other, but another generator of the Picard group. Okay. Okay. So what I'm going to do with this? So this will be essentially the subvariety of the Hilbert scheme that I would like to use to prove, at least in some cases, the unirationality of conic bundles. And so you see, this is defined on a single Sx, okay? But actually, the canonical class is defined over X, and also F is defined over Fs as soon as I have a linear system on W that intersect my lambda in just one point. So let us assume it. So assume there exists a linear system M, base point free, linear system with m dot lambda equal to 1. Okay. Then, well, you see, whenever I pick, so for any d, well, not for any, but for a general. For a general d in M, if I consider, let me write it in this way, so the preimage, or the pullback if you prefer, but I prefer to consider it as the preimage. This is again another conic bundle. In dimension 2, and therefore by its n theorem, if you want, or by Graber-Harris star, it has a section. It has many of sections, so it's plenty of section. So has plenty of sections. And so if we fix one of these sections, so if gamma is a section of then gamma intersected Sx is just a point. It's just, let me call it gamma x, a point. And so you see, using this base point free linear system M, I'm able to define points on any Sx in such a way that they're well defined on the generic fiber S eta. So essentially, I'm saying that having M gives you points on S eta. So i.e. S eta is full of points. Okay, and therefore I can well do the same construction on S eta. The only problem is that I'm doing this with the empty set here because, as we will see, I mean, this is a bit. This is not coming from point on S eta on Sx. So this allows to do the same construction on S eta with B equal the empty set. And so I may define something like R, let's say gamma 1 up to gamma m, empty set AD S eta as before. So let me write simply as so irreducible rational inside oh no, let me do it in a not such a short way because I want to so C X okay, C irreducible rational in I of I put it C eta to the 2a of minus a ks eta plus df, where zeta are the generic points of the sections gamma I. Okay, so gamma I gives me a point on S eta, and so I can choose this point, and so I'm considering linear system of rational curve on this guy, and this will be clearly, if you look at them inside X, these are surfaces having multiplicities 2a along my sections gamma 1, gamma m. That this is well defined. So this is well defined on S eta. Because this is the one I'm going to work with. Because the main difference between these two is the B. Okay, so here I have B, so I also have B, and here I can't put B, but the reason maybe is a bit obscure now, and I hope to make it clearer in a while, but just in a few seconds. Okay. So if you are with me that this is well defined, then I'm fine for the moment. Okay. Okay. So this is nothing else. So this R gamma 1 gamma m ADS eta is nothing else than let me say the generic point, well, yeah, the generic fiber of some R inside ILB X over P1. Okay? And let me stress here, remark, that if A is strictly positive, and this will be clearly all the case I'm interested in, the general element is transverse to pi. And I'm really stressing this point because this is the crucial part of this construction. So now we are able to translate the unirationality of X into a rational connection statement about this R. So this is the theorem. So assume all the hypotheses are fulfilled. So with this I mean I have my lambda, I have my m, okay? X is a threefold conic bundle with all the structure. Huh? And there exists such R, so R is the one over there, such that Rx, the fiber over the general point, is rationally connected. Okay? So then X is unirational. Once we have done all this definition and notation, it's not that difficult because this is essentially Enrique's criterion, which is again essentially base change, plus Greber-Array star result. And I will show you in a moment. Okay. So proof, so by Enrique's, X is unirational if and only if there exists a divisor D rational. Actually unirational is enough, but since it's a surface that's equivalent, exists D in X rational and transverse to pi. So my notation are always consistent. So pi is always the conic bundle structure of my X. And this simply, I mean, I don't have that much time, so I'll skip, but that's simply base change. Okay. And then by Greber-Array star, we have a one-dimensional family of rationally connected variety, and therefore there is a point. So there is a section. So by Greber-Array star, R has a section. And this section is nothing else than you know, picking a rational curve on a general, over a general X of this morphism on to psi. And so this gives you a surface which is covered by rational curves, but for surfaces being covered by rational curve is equivalent to being since dominates P1 is equivalent to being rational, and therefore R is a section, and this section is the surface we are looking for, is D. Well, not is, but gives D. Okay? So this is the first step. We translated the unirationality of X onto, that's the price I was saying to you, onto a rationally connected statement of some sub-variety of this Hilbert scheme. Okay. So since the Hilbert scheme of this guy is not that nice, and even the one on Sx is not that nice, I prefer to do a second step and going from this Sx to P2. And so the second step from Sx to P2. And this is very nice, at least from my point of view. So we have our Sx. So maybe I have still it on some blackboard. No, I erased everything. So if you remember, Sx is simply Fe blown up in some point. Okay? So I have not a canonical way, but I have a very nice way to go from Sx to P2. So first I blow down reducible curves, and this takes me on to Fe. And then I may perform absolute value of E minus 1 elementary transformation. And this takes me to F1. And then here I have a choice. And that's really important for what we are going to do, I think, tomorrow. So I can either blow down the minus 1 curve here and go to P2, or I can perform another even number of elementary transformation. So 2k elementary transformation. And go again on F1, and then go down to P2. Okay? And if we only look at this part of the diagram, what do we have? We have that we are performing a de Jonquier transformation centered in a special point. And so this allows me to define everything essentially up to the Jonquier transformation once I am on P2. And this is really important, because now I have to show you that I blow down one component of the curve, and so I go to Fe. Yes, yeah, I said. So everything here is, how to say, natural but not canonical. So I have plenty of choices. Okay? And that's it. So the choices here are due to the fact that I can't have this on S eta. No? If I have this on S eta, then I have a canonical way to go to Fe, but then my triple is rational. Okay? And so that's a bit technical, so I will skip it completely, but I will show you what happens. So we start on Sx with something like that. So we start on R A empty set AD on Sx. And then performing this gives you a birational map onto R AB AD on Fe, where this B is just the set of points that I have to blow up on Fe to get Sx. So where Sx is the blow up in B of Fe. And then during this elementary transformation business, I get, let me say, some A prime, B prime, A keeps the same, and here I have D minus A, E minus 1 plus 2k. And this is on F1. Okay? So there is a complete way to control the behavior of this object along this transformation. And if everything is okay in the end, then all these maps are birational maps. So I can substitute my original variety Ra with the one on F1, and then it's not that difficult to see that this goes down onto something that I can call R B A3 plus D minus A minus 1 plus 2K on P2, and these are just so where the latter is just a set of irreducible rational curves in I of, let's say, P naught, let's say D minus 2A union B to A of D. Okay? And so this is R B A D P2. Okay? So essentially what I'm, in the end, I have a sublinear system of the linear system of curves of some degree D, which is this D, and I can control it very well. Having a unique point of multiplicity D minus 2A, and B points of multiplicity A, where the length of B is nothing else than delta dot my lambda. So the degree of the discriminant curve with respect to the pencil of rational curves I'm choosing at the beginning. And so we translate the unirationality with the rational connection of something like this. And now you have the third step, so you have to produce some rationally connected stuff of that type. So now you are on P2, you have no more excuses, so you have to work on this. And unfortunately, that's the weak part of the argument, as usual. In the end, you don't have a very much satisfactory answer. But so in the end, one can prove that, well, the following. Let me call it lemma. So let B inside P2 minus P naught be such that the length of B is 7. Then there exists a de Jonquier transformation centered in P naught such that R, the de Jonquier transformation, let me call it F of B for 11 is isomorphic to P1. Okay, and I'm not going to prove this, even if it is not difficult. I'm just remarking a couple of things about this. So the two things I want to remark are the following. So first, F is crucial. So it's not true, because the point is that this B can land, if you don't apply this de Jonquier transformation, this B can land in P2 in a strange way and in a spatial configuration that doesn't give you the right answer. But up to a de Jonquier transformation, which can be done, as I said, via this supplementary set of elementary transformation, you can always put this set in a nice enough situation. And the second remark is that maybe, I mean, someone of you already realized it. So this 7 is the number of points, well, 7 plus 1, because we have P naught going around there. 7 plus 1 is just the number of points you have to blow up to get a del Pezzo of degree 1. And on a del Pezzo of degree 1, is if the points are in general position, you have essentially, well, you always, if you have a conic bundle structure, then you always have also another conic bundle structure induced by the Bertini involution on the elliptic curve, okay, associated to the fixed point of the anticanonical class. And this is essentially, from some point of view, the Bertini involution applied to the canonical system. Well, to the conic bundle to the original conic bundle. So essentially, this is related to Bertini involution on the conic bundle structure. Associated to minus k of, let me put it right in this way, to the anticanonical class of the del pezzo surface of degree 1. Okay? And clearly this works only when the points are in general position, because if the points are not in general position, then you don't really have a second conic bundle structure. Okay? And essentially the de Jonquet transformation allows you to put the points always in a general enough position so to get this. A different way to see this P1 is simply take a pencil of conics and then apply some Cremona transformation in some precise point, and you get this linear system of rational curves. And probably you realize that P1 is rationally connected. And so this is the sub-variety I'm looking. Oh, I forgot a P2. This is the sub-variety I'm looking for, and tomorrow I'll show you what is the output of all of this construction for the unirationality of some special conic bundles. That's similar. That's similar. So you see, if is this a question? Because you have to pick the microphone.
I mean, if the field was not closed, then you could possibly ask an interesting question somewhere. About the tensor 1.
Yeah. Yeah. That's it. So let me see if yes, I have it there, I think. So the point is. This is over a non-algebraically closed field. So essentially, what I'm saying is that this one, when that number is 7, this one is not the del pezzo of degree 1, but is the resolution. So in general, this is only in f and big. So the canonical class is only in f and big if the points are not in general position. So when it is in general position, then since it has a conic bundle structure, as I said, it has another conic bundle structure, because so the anticanonical class is ample, and so you have 2 rays in the Morricone, and so one is the conic bundle, and the other one is the other conic bundle structure. And so so that's already the transverse surface, rational surface I'm looking for. But when the points are not in general position, this is only a resolution of a singular del pezzo surface over a non-algebraically closed field. And that's if you want. So my point, essentially, my point is actually to try to avoid, but that's for my weakness, not for not for some more higher purpose. Trying to avoid the non-algebraically closed field and try to translate there, because there you are on an algebraically, so on P2 over an algebraically closed field. Okay.
Further questions? So. So I'm a bit lost in the notation. So this last thing here, this R, are there curves of what's so degree 11?
11
with multiplicity something, multiplicity 4 at points of f of b?
Yeah. So these are. That's a good question. So these are degree 11 with 1 point of multiplicity 3 and 7 points of multiplicity 4. So A is 4 in this case. So 2a is 8, 2a plus this one plus 3 is 11, and that's the...
So yeah, rational curves.
These are the rational curves I'm, in the end, able to produce.
Well, if not, let's thank.
Thank you.